planes, and this is sort of the last bit of vectors, but it does require us to get through a little bit of stuff. The first part that's important is just to see how the equations that we use for planes are sort of built up, but you're probably not going to be asked a question like this. But at the moment you can see on the screen just really how planes fit into our whole three-dimensional space. Okay, so the plane is that 2 dimensions. We're used to graphing things on the XY plane. Okay, but in 3 dimensions, obviously, we have the Z-axis as well, and a plane can be on an angle through any of the 3-dimensional space, but it's a flat surface. So what we would say is that a vector is parallel to that plane if 2 points on that vector, okay, lie on the plane. So you can see the diagram that's there. So we're going to use that idea, but go one step further to help to see how the equations are built up. And we're going to consider the diagram here and think of 2 vectors that are both on the plane, so they're parallel to the plane, okay? But those 2 vectors are not parallel to each other. They need to be non-parallel to each other. So we've got 2 planes, 2 vectors, A to B and A to C drawn on there. Now, if we look at this diagram here, this is just a plane in space, the blue plane there, and you can see there's 2 points A and R that are on that plane. We've got 2 vectors, V and W, that are drawn. Now, they're not a vector that goes from A to R. Okay, they're just 2 vectors that are on the plane and they're not parallel to each other. So V and W are parallel to the plane. Okay, what we want to consider is a point, not a point, we want to consider, let's just put a spot there and call that the origin. Okay, so we can have a vector O or origin to A, okay, and we'll often use A as our symbol for that because the capital A, remember, is representing a point, and now we have a vector going from the origin to A. And we could also think about the origin all the way over here to the point R, which we'll call that vector. Now, those 2 are very similar to when we were coming up to the vector equation of a line. Same sort of thing, because if you look at the diagram that we've created there, then you can imagine that if we wanted to deal with something with those, then we could say that this vector, that is actually the red one that I've drawn there, goes from A to R and is on the plane, then that relates, or we can relate that to vector A and vector R, okay, coming from the origin. All right, so there's 2 points. But the thing that I want you to think about is, can you draw a vector, could you, not can you do it on this, but could you draw a vector diagram, or could you work out the vector that's red there, okay, could the vector, so vector A, R, could that be made up of component or parts of vectors V and W? Could you get from A to R by adding V's and W's, maybe not whole values of V's and W's? Yes, you can get there. You could get there, and like, you know, looking at that diagram, it might be like, I don't know, 3 V's and 2 W's or something like that. Okay, looking at that diagram. Now, if I move that point R anywhere on the plane, could I do the same thing? Yes. Yeah, I can make it up of scalar multiples of V and W, like adding scalar multiples of V and W, and I could get from anywhere from A to R. So it's like we could plot any point on the plane by using those 2 vectors.
Okay, so that's what's important in there. It's also the reason why back here we say that those two vectors cannot be parallel. Because if they are parallel, then we wouldn't have a way to be able to move sort of sideways to get there. If they're both in the same direction, we just keep going in the same line, we wouldn't be able to move sideways to get from one point to the other. But if they're not parallel and on the plane, we can use multiples of it. So all of those ideas come to, we put them together. I'll probably jump to the first idea we're using. This is the vector equation of the line. Okay, and you can see that R, the position vector of any point on the plane, so here, can be equal to, all right, so if we're going to get from the origin to R, that position vector, R, off my diagram, okay, we can get there from here to here. We could get there by going from the origin up to the point A that we know, and then adding a certain number of V's and W's to get to that point. And no matter where R is, we could do that. That's what this equation says. Okay, we're going to have the vector R is equal to the vector A plus, a certain number of V's plus a certain number of W's, remembering that S and T could be non-whole numbers. We don't have to have whole numbers to get there. Okay, so that would be a vector equation of the plane. That would give us any R vector that sits on the plane, or any R point that sits on the plane. Okay, that by itself may not be that useful. Okay, we have uses for it. What we're going to go to is then use this idea here, just try and get on the screen, which gives us a much more useful equation to deal with. And we start by saying, okay, if I've got two vectors that are parallel, one thing I could do is draw a normal, or calculate a normal, a 90 degree, a perpendicular to those. And if we look at this, we'll zoom in on that diagram there. If we look at that diagram, our V and our W are drawn, so they're parallel to the plane. So there is a vector that can be drawn that comes out 90 degrees, and it's going to be 90 degrees to both of those, and it will also hence be 90 degrees to the plane itself. Okay, and we already have the maths to deal with that. Okay, we already know that if we have the cross product of V and W, okay, then the vector that we get is 9 degrees to that. That's what we get. So if we've got two vectors on a plane, cross product, we get the normal to the plane. Okay, and then got this piece of information that says that since n is perpendicular to any vector on the plane, so we've got that, an equivalent vector equation of the plane is this. So instead of writing the vector equation as it was before, okay, we could say that the scalar product, so n crossed with the difference between these two vectors is equal to 0. Remember that if you get the scalar product, then the when it's 0, then they're 90 degrees. Okay, so we need to go back to this diagram. Okay, hopefully that's big enough to be able to see. So if we have the normal to this plane, okay, then R take A. Okay, so if we've got R, which is here, okay, and we take A, all right, that's a bit hard to think what that's going to look like on that diagram, but effectively we end up with the vector that goes from A to R. Okay, so that is on the plane, hence the normal must be perpendicular to that vector. Okay, all right, so this is the vector that sits on the plane, this is the normal, so that must equal 0. Okay, and then we can go, and this is the part that's the most important, this line here, because we're going to use that
in the next part, and you'll probably never think of it like this, and after looking at it like this now, but that means that if we expand out, if we do the vector algebra on this line, okay, we have n dot r take n dot a equals 0. So n dot r equals, and they've just written it as a dot n. So that's just using the algebra for the dot product. Okay, why is that important? That is how we get this, which is what we're going to use. Okay, so we've got n dot r. Okay, so if I have a plane which has a normal vector of a, b, c, that's the normal, and we're dotting that with r, okay, which is a point somewhere on our plane. We don't know where it is. Okay, so I'm going to actually put that on here as well and say that the point, the vector r is just going to be x, y, z. Okay, the vector r is x, y, z because that's just a point somewhere on the plane. So if I did n dot r, it becomes a times x plus b times y plus c times z. So that's that side of the equation. Okay, and it's equal to a dot n. Okay, a is really, this is point A. Oops. This is point A. Therefore, the vector A, because it's from the origin out, is going to be capital X, capital Y, capital Z. Okay, so important that there's using that's why they're using the capitals there. So n dot by A becomes A lots of capital X, B lots of capital Y, and C lots of Z. Okay, but you can see here that they then say that that equals D, and the reason that they say that equals D is because this side of the equation, if you have the normal vector and its numbers, and you have a point, okay, and its numbers, then this side here is going to come out as a value, as a constant value. Okay, so you put those in, you get a constant value. So they've said that it's equal to D. Okay, so effectively, you could just consider that the vector equation is this part equals D. All right, and that's often how you'll see it. You'll see values like 2x plus 3y take 7z is equal to 2. Okay, and that will be a vector, an equation, not a vector, equation for a plane, and it's the Cartesian equation. Right, you're probably not going to have to build that up, but that's where it all comes from. What we're going to see is things like this. Okay, from a very simple example, which gives you, just like that, that formula says, it gives you the normal vector. The normal vector is 1, 2, 3. And it passes through a point. The plane passes through a point -1, 2, 4. Okay, so we know that that point lies on the plane. We know that's the normal. All we're going to do is remembering that it is n dot, just broken that. I don't know what happened. Where was I? I don't know why that stopped working then for a sec. We're doing n dot r is equal to a dot n. Okay, so our n dot r is going to be these and these together. Okay, so sorry, our n dot r is not. Our n dot r is going to be this with our x, y, z. Okay, so we've got 1 there, 1 lot of x, plus 2 lots of y, plus 3 lots of z.
and it equals, on the constant side, we've got our a dot n. This is our a points, which is effectively going to be the vector a, minus 1, 2, 4, and we're going to multiply each one, or dot product by those. Okay, so minus 1 times 1 is 1, 2 times 2, and 4 times 3. So there is our equation. Sorry, I didn't realise that was so small on your screen. Fill that back up again. We could go further, okay, and we could say let's put that into a vector form, okay. So this one says we've got to find the equation of a plane through 3 points. So much more work involved in that, okay, but very doable. That's all we need the first part though, okay. The first part says that our R here, okay, is going to be equal to the point that we know, okay. Now they have chosen, for whatever reason, they've chosen point C as being the fixed point on the plane, but we could choose any of them, assuming they're all on there. So this is our fixed point, all right. So it's the origin out to C, okay. And then the two planes, they've already worked that out. The two vectors, they've done A to B and C to B. Okay, and so they've got those two vectors. S and T, remember, those two are just some sort of value that are going to multiply the two vectors so that we can move from one point to another. So we don't know what they are. They are two parameters. They would be they need to be different letters. They could, by chance, end up being the same value, but they certainly don't have to, and most times they wouldn't. Okay. And then for part B, we would need to work out their normal vector. Okay, and so you need to do a cross product. They've done the cross product for the two vectors that they've decided to work out, which makes sense. Okay, they have got the normal. Okay, then they've just placed that into the same stuff as what we did in the previous example. Okay, it would be important when you're doing work probably to do this, check that the 3 points all work for that equation. Okay, so you can put points into here, right, at the end, and you can say, right, well, does point A fit? I put my X, Y, and Z in. Does it equal 19 on both sides, etc. In a test, probably unless it tells you you have to check them, I'm not going to expect that. I mean, it's sort of work on top of what you've already been doing. Okay, so that's the sort of the majority of the start of the plane stuff. There are questions. I can't remember what this is. Is this 6H? This is. There are some questions that you can do from that. We might need to have a look at some more in our next lesson.